In 1737, Leonhard Euler was playing with an infinite sum, 1 plus 1/2 plus 1/3 plus 1/4, continuing forever. He already knew the answer, pi squared over 6, a bizarre, irrational number hiding inside what looked like a simple pattern. But Euler noticed something stranger. If you write this sum differently, as 1 over n to the power of s, where s is any number, you get a machine, a function, a single equation that encodes something fundamental about how numbers are spaced across infinity. He called it the zeta function. And then Euler did something remarkable. He rewrote the zeta function, not as a sum over all integers, but as a product over all primes. Every single prime number contributed exactly one factor, and their product equaled the same thing. This was the first hint. The zeta function and the primes are the same object, seen from different angles. In 1859, Bernhard Riemann took Euler's function somewhere no one had gone before. He asked, what happens if s is not just a real number, but a complex one, a number with both a real and an imaginary part? Suddenly, the zeta function became a landscape, a surface draped over the complex plane, rising and falling like terrain, and Riemann found something that stopped him cold. The function has zeros, points where it collapses to exactly nothing. Riemann found some trivial ones at the negative even integers, but then he found others, non-trivial zeros, and they all appeared to line up on a single vertical line in the complex plane. The line where the real part of s equals exactly 1/2. He could not prove it. He did not even really try. He simply noted it and moved on. That offhand remark became the most famous unsolved problem in mathematics. Here is where it becomes extraordinary. Riemann proved that the exact locations of these zeros, their heights on the critical line, act as frequencies, as musical notes. If you take each zero, treat its imaginary part as a frequency, and add up the corresponding waves, you get something remarkable. You reconstruct the distribution of prime numbers, exactly, completely. The irregular, apparently random scatter of primes across the number line is the sum of infinitely many perfect waves, each one tuned to a zero of the zeta function. The primes are not random, they are a symphony, and the Riemann zeros are its score. In 1972, mathematician Hugh Montgomery was at the Institute for Advanced Study in Princeton, working on the statistics of Riemann zeros, how they are spaced relative to each other. At tea, he mentioned his results to physicist Freeman Dyson. Dyson went pale. He recognized the formula immediately. It was the same distribution that describes the energy levels of large atomic nuclei, specifically, a class of random matrices from quantum mechanics called the Gaussian unitary ensemble. These two things, the zeros of an abstract function about prime numbers and the quantum energy levels of real physical matter, obey the same statistical law. This is not a coincidence that has been explained away. It remains one of the deepest unexplained connections in all of science. The zeros of the Riemann zeta function appear to be eigenvalues of some undiscovered physical operator, some quantum system we have not found yet. The primes may be controlling something in nature, and we do not know what. The deeper you pull on this thread, the more of physics and mathematics unravels with it. The same zero statistics appear in quantum chaotic systems, in the scattering of electrons, in models of disordered conductors. Some physicists now believe that if the Riemann hypothesis is ever proved, the proof will come not from pure mathematics, but from physics, from discovering the actual quantum Hamiltonian whose eigenvalues are the Riemann zeros. There would be a real, physical object whose quantum energy levels are exactly the prime numbers. Think about what that means. Over 2,000 years, mathematics has been circling this mystery. Euclid proved the primes are infinite. Euler connected them to a series. Riemann connected that series to a landscape of zeros. And in 2013, a nearly unknown mathematician named Yideng Zhang proved for the first time that there are infinitely many pairs of primes separated by a bounded gap. The ceiling has started falling. Nobody knows what drives this, but the zeros are watching. The Riemann hypothesis, one sentence, the most important unsolved problem in mathematics, carrying a $1 million prize from the Clay Mathematics Institute. Verified computationally for the first 10 trillion zeros, all of them, without exception, sitting exactly on that line. but unproved, for over 160 years. If it is false, if even one zero sits off that line, the primes dissolve into chaos. The encryption protecting your banking, your messages, the entire architecture of the digital world rests on assumptions about prime behavior that only hold if Riemann was right. We are betting civilization on a conjecture. The prime numbers were always there, 2, 3, 5, 7, older than any human language, older than any physical law we have written down. But Riemann showed us that beneath their apparent randomness, there is a score, a set of frequencies, the zeros that compose them perfectly, and those same frequencies, impossibly, appear to be written into the quantum fabric of matter itself. Whether that is coincidence, or whether the universe is, in some deep sense, built on prime numbers, we do not yet know, but the music is playing. It has always been playing. We are only just learning to hear it.